Aloha! In this video we will discuss whether we can scientifically prove a theory or a model. The term, scientifically proven, is often used colloquially. This usage has been popularized by journalists and is prevalent in the media. Many people readily accept terms like scientific proof and scientifically proven without critical examination. Sometimes even scientists use the terms prove or proof in a loose sense, such as proof for climate change and proof for evolution. However, it is not technically accurate in the context of empirical science. In formal logic and mathematics, proof has a specific meaning. It involves logical entailment, a deductive process where conclusions necessarily follow from axioms and premises. If the premises are true and the reasoning is valid, the conclusion must be true. There is no room for doubt. If A then B, A is true, hence, B follows logically. Specifically, if it rains, the ground will get wet. It is raining, therefore, the ground must be wet. However, in empirical science, conclusions are based on observations and experiments, which provide data and evidence only, but do not lead to absolute certainty. Theories are evaluated based on how well they explain and predict phenomena, but they remain provisional because new evidence or perspectives could challenge them. In data analysis, a theory or a model that consistently fits observations and withstands repeated testing is said to be well supported or empirically adequate. To be specific, in hypothesis testing, at most we can confirm or affirm that the data and the model fit each other, but we cannot claim that the theory is proven. For example, the theory of quantum mechanics or evolution is supported by extensive evidence, but scientists remain open to revising these theories if new evidence or insights emerge. If not, then it will become dogmatic. A key principle in science is falsifiability, a concept articulated by philosopher of science Karl Popper. According to Popper, for a theory to be considered scientific, it must be formulated in a way that allows for the possibility of being falsified or negated through empirical observation or experiment. This requirement for testability contrasts sharply with the absolute certainty implied by the term proof, which belongs more to mathematics and formal logic. A classic example illustrating the importance of falsifiability involves the claim that all swans are white. For centuries, this statement seemed consistent with observations made in Europe, where only white swans were encountered. Later, the discovery of black swans in Australia provided evidence that falsified the claim. This example demonstrates how empirical science works. Rather than proving statements with absolute certainty, it tests them against evidence, always leaving room for revision or refutation. The inability to achieve conclusive proof in empirical science is connected to the problem of induction, a concept explored by philosopher David Hume. Induction refers to the process of drawing general conclusions based on specific observations. Let's revisit the same example. Observing many white swans might lead to the generalization that all swans are white. But this finding is inherently uncertain because future observations, such as finding a black swan, could contradict the conclusion. Following this line of reasoning, in an open universe, any event has a remote probability of occurring. In classical statistics, the p-value represents the probability of observing the test statistic, or more extreme values, if the study were repeated infinitely in the long run, assuming the null hypothesis is true. However, some authors have erroneously reported a p-value of absolute zero, despite the fact that a p-value can never truly equal zero. This error often arises from truncating decimal places and misunderstanding that statistical inference inherently lacks absolute certainty. In the field of data analysis, it is generally agreed that the term confirm is used to reflect the conclusion that the model and the data fit each other. Some methodologies aim to fit the model to the data and some are opposite. Nonetheless, this subtle difference is beyond the scope of this video. Some philosophers go further, arguing that empirical fitness supports an anti-realist stance. For instance, in his influential book The Scientific Image published in 1980, prominent philosopher of science Bob Van Frossen argues that the goal of science is not to discover ultimate truths, but to develop theories that are empirically adequate. A theory is considered empirically adequate if it correctly describes observable phenomena, what we can perceive and measure. Beyond this, Van Frossen contends, we are not justified in claiming that the entities posited by the theory are real or that the theory itself is true. In his view, science should limit its ambitions to saving the phenomena, without making metaphysical claims about reality. The debate between realism and anti-realism is a profound and complex one, and a full exploration lies beyond the scope of this discussion. Nevertheless, I believe it is possible to adopt a compartmentalized and pragmatic stance that incorporates elements of both realism and skepticism, depending on the context. For example, in everyday situations, such as watching a weather report and experiencing a hot day, it seems entirely reasonable to say, it is really a hot day, based on direct sensory experience and empirical confirmation. On the other hand, when dealing with abstract scientific theories, I tend to hesitate before claiming that a theory is real or true in an ultimate sense. Theories often involve unobservable entities and constructs that, while useful, may not correspond to objective reality as it truly is. This perspective underscores the importance of humility in science. At its core, science is a process of inquiry, not a path to absolute certainty. No theory can be definitively proven in the same way a mathematical theorem can. Instead, we can only confirm that the evidence is sufficiently strong to justify belief, support a decision, or guide action. Recognizing this provisional nature of scientific knowledge fosters a mindset of openness and adaptability, essential qualities for progress in both science and philosophy. Thank you for watching. Mahalo.